Today's speaker is Mr. Devang Falor, currently doing his PhD at the Indian Institute of Science from the Center of Atmospheric and Ocean Sciences.
The outline of the talk is as follows. I shall first try to cover the basics of fluid mechanics and some applications, and then I will slowly progress on to my main field of research, which is geophysical fluid dynamics and oceanography. And then after briefly talking a bit about GFD and oceanography, I will then transition into cyclones and how they impact the ocean, and especially Bay of Bengal, and what is the ocean's response towards these kind of extreme atmospheric events. The third regime is very interesting. It's called a transitional flow, where the flow remains laminar up to some region, and then it slowly begins to transition from laminar to turbulent. So it goes unstable, and it creates these nice streaks, or these nice vortices, as we call it. So this is called as a transitional flow. These two trailing vortices create what is called as clear air turbulence. This condition is known as atherosclerosis, and blood flow inside the arteries is very, very interesting because of four major reasons. One is that blood is a non-Newtonian fluid, and the size of these individual granules are of about 1500 kilometers, and there are these millions of granules on the sun's surface. So what this just slight infinitesimal perturbation did is it blew up, and all of the simulations that he did, he got very, very different results, which makes the system extremely unpredictable. This is geophysical fluid dynamics. This is a branch of fluid dynamics which deals with large-scale circulations or geophysical flows. Stratification means that there is a property of the fluid which is varying across depths, and that variation of property creates a variation in density. So this is just because of the upper ocean turbulence that you are seeing this constant values of these three quantities. Air will come and converge, and in the northern hemisphere the air comes and goes around in anti-clockwise fashion, and then it spirals inward. They are going in a clockwise direction and they are spiraling inward. This is the southern ocean around Antarctica. Right from the year 1960, that you can clearly see that the SST has been slowly and gradually rising. The anomaly is slowly and gradually rising, and it has gone up to 1 Fahrenheit. And the top and the bottom yellow, orange lines actually denote the error bar. So the velocity has an exponentially decaying term for the magnitude, and the velocity, and that exponentially decaying term is multiplied by a sinusoid or a cosine term for the change in direction. Sea surface velocity, you can clearly see that the velocity is quite high in the equatorial regions. There's a lot of turbulence in the equatorial regions, and as we go more and more towards the poles, the velocity decreases. The domain actually represents an idealized southern ocean. As we go more and more towards the north, we can clearly see that the temperature is increasing. So Bay of Bengal is very, very special in a sense that it receives heavy rainfall and heavy river runoff. So it is one of the freshest waters amongst all the tropical oceans. Then as the cyclones progressively move towards a certain coast, suppose it is moving towards Bangladesh or towards Orissa or Bengal coast, so this seawater will continue to rise and move as sort of a wave. And that wave, when it hits the coast, there is a lot of inland flooding, as we call it, and that is called as storm surges. This cyclone this cyclone was formed near the coast of Myanmar, and then it gradually progressed towards India line, which is data 𝘎𝑖𝑟 141, when the cyclone has arrived and created a lot of mixing. The sea surface temperature has decreased, and we can see that this temperature is homogeneous up to 50 decibars. This n-square actually denotes or depicts the density structure within the ocean. So wherever this quantity is 0, the density is almost homogeneous. So you can clearly see how much of this cyclone is trying to bring up the cold waters from below to have a 3 degrees Celsius cooling. What exactly is happening at the air-sea interface? The interface is very, very important because through the interface, we can say that the air and the ocean talk to each other.
Is it possible to integrate AI-based approaches into your modeling and bring in more predictive solutions, or are there any challenges that you see? So basically what happens is that, as you mentioned, that Navier-Stokes equation is notoriously difficult to solve, and there is uniqueness problem and all those things. So, but now there is an increasing interest in AI community regarding solving these kind of equations. So do you see in future, if it's possible that to completely do away with these physics derived equations and bring in picture AI based solutions?
Yeah, thanks for the very nice question, Vinayak. Good to see you again, by the way. um, so it's a very nice question, and there are right now people working using these machine learning techniques. There is a very active project there in Australia currently where my guide is, and he's also involved in that project. What these people are doing is these people are taking whatever data that we have. Suppose we have some in situ data, suppose we have some observational data, and then they are running that through machine learning stuff so that we can have a better predictability. Again, this comes to the same concept of simple scaling arguments. Based upon whatever data that we have, we are trying to construct a simple scaling. But yes, people are actively working using ML and AI techniques to so that we don't have to do these expensive simulations and these expensive observations in the future. We can predict very well, and I mean the general predictability is very good.
Okay.
So yes, people are working on ML and there are these very nice quotes by the famous scientists. The first quote is that when I meet God, I'm going to ask him two questions: why relativity and why turbulence? And I really believe that he will have an answer for the first one. It's some people credit this quote to Werner Heisenberg, who is a famous physicist. There's some people credit it to Horace Lamb, who is a famous fluid dynamicist. But in all essential, essentially, it means that turbulence is a very difficult problem, and even people like Heisenberg, they have dipped their hands in Navier-Stokes and they have burnt it, as one of my professors used to say, as one of the professors that I studied from used to say. And the second quote is that turbulence is the most important unsolved problem of classical physics. So it's by Richard Feynman. You can clearly see Richard Feynman here towards the extreme right. He's a very famous, I think one of the most famous physicists, really brilliant guy. And classical physics at the middle of the 20th century, or even at the start of the 20th century, people sort of stopped doing classical physics. That's just because of the rapid invention and the rapid ideas that were being sprung upon of quantum mechanics, of relativity, of all other interesting physics stuff. But when it came to turbulence, the classical, I mean, people in physics or people in any science community, they are still not able to solve this age-old problem. So Richard Feynman commented in a very beautiful quote, which is that turbulence is the most important unsolved problem, and people are still trying to look into that. And with these quotes, I would like to conclude.
So if you are an enthusiastic researcher and you want to share your work with the rest of the world, we are there for you. There's Researcher on Web. Currently, there are two opportunities. You can either be a part of a live webinar session on Sunday, as Devang was today, and you can interact with our live audience, or you can publish a semi-technical research blog in our platform and maybe even reach thousands and millions of readers in your field.